Hello, good evening everyone. Welcome to I think mostly the last session for the course Machinery Fault Diagnosis and Signal Processing. So this week we will actually look at the questions for the entire questions from the entire syllabus. Today I have around 20 to 35 questions which we will see one by one, but they are from the entire syllabus. Okay, so yeah, let's begin the session. First question for today is the question is which type of maintenance is also known as condition based monitoring or maintenance. Or maintenance. The options are predictive, reactive, and preventive. So which type of maintenance is known as condition based maintenance? Predictive, reactive, preventive, or none of these three? The answer is predictive maintenance. So in condition based maintenance we actually have sensors or transducers that track some characters of the operation, either vibration or you can see the temperature or vibration or temperature or pressure levels or sound, track some of these characteristics, and if those characteristics match with some certain behavior then you do the maintenance. So that is why it is a condition based maintenance or predictive maintenance. In reactive maintenance you do if there is any failure, so after the failure has happened then you do the maintenance, so that is called, that is why it's reactive maintenance. In preventive maintenance, even if there is no failure or if there is no characterization track of the system, you just do every few months periodically, that is the preventive maintenance. So in the current question is which is condition based maintenance is the predictive maintenance. Okay, yeah. So let's look at the second question. So what should be the RPM if the ranks of severity is 5, occurrence is 10 and detection is 2? So RPN actually means risk priority number, and it is calculated by the product of rank of severity into rank of occurrence into rank of detection. So how severe it is, how frequently does it occur, and the rank of detection is if it is very easy to detect, then it will have low rank, and if it is very hard to detect, then it will have high rank. So here it would be 5 into 10 into 2, so 52 is 100. So the RPN in this case is 100. The maximum value for the RPN is it can take up to 1000. So that means that is the worst case scenario, very bad. It has very high risk. So you have to prioritize maintenance for that machine. Okay. Let's move to the next question. Two springs have stiffnesses of 1000 nanometer and 1500 nanometer. What is the equivalent stiffness if they are connected in series? The options are so what should be the answer? Here the springs are in series and each individual spring stiffness is given. So when you have two springs in series, K1, K2, then the effective stiffness would be K1, K2 by K1 plus K2. So here we have one as 1000, other is 1500. So 1000 into 1500 by 600 Newton per meter. Okay, so the answer is 600 Newton per meter. So this is when you have springs in series. But if they are in parallel, then K equivalent is K1 plus K2. Okay. So this is for the case of springs in series, and this is for the case of springs in parallel. Let's move to the next question. So if the characteristic roots of a single degree of freedom spring mass damper system have real positive roots or are real positive roots, then what should be the system's response? Stable, unstable, asymptotically stable, cancel. So this is a single degree of freedom spring mass system. So in that case, and there might be some damping C. So for such system, the governing equation we can write as equal to 0, and assuming x is equal to a into e power lambda t as a possible solution, this equation becomes to 0. So this would give the roots for lambda as so. In these cases, usually we have damping factor given as c by 2 root km. This is the damping coefficient, and the natural frequency omega n is root k by m, and the critical damping coefficient is 2m omega n or 2 root k. Okay. So these are some of the cases, and with this you can actually write lambda as minus omega n into zeta plus or minus root over 1 minus zeta. So this is the damping factor, this is the natural frequency, this is the critical damping coefficient. Okay, this is a single degree of freedom spring mass damper system. Now, based on the roots, it is based on the solutions for lambda. If the roots are real, that is when c square greater than 4 mk. So if roots are real, that is c square greater than 4 mk, or zeta greater than or equal to. Okay. So in that case, the roots would be positive. Oh no. So the roots would be real if c square greater than or equal to 4 mk, which is same as zeta greater than or equal to 1. Okay. Now, if the roots are real and positive, then the system would be unstable. It will oscillate so much and it will fail. And if the roots are real and equal, so that will happen when c square equal to 4mk or zeta equal to 1. So in that case, we will have critical damping and stable system. Case where roots are real but negative, then this would happen when c square greater than equal to 4mk. This will happen when zeta greater than 0. So, so positive or negative depends on how c and c square minus 4mk are related. But if the roots are real and positive, it will be unstable system. Roots are real and equal, then it will be critical damping system. If they are real and negative, then it will be over damped system but stable. And if the roots are imaginary, so if the roots are imaginary, then it would be a damped system and it will be a stable. So 0 less than zeta less than 1, then it would be an under damped stable system. Okay. And if zeta is 0, then it would be an undamped system, which is asymptotically stable. Okay. So in this case, we have roots are real positive roots. So real positive roots, the system is unstable. I hope this is clear. So single degree of freedom, this is the governing equation. From the governing equation, you can estimate lambda. Now, based on the kind of roots lambda is, if roots are real and positive, then you have unstable system. If the roots are real and equal, then you would have a critically damped system, and roots are real and negative, then you would have a over damped system. If the roots are imaginary, that means the damping factor is 0 to 1, then you have under damped system. If damping is 0, then you have undamped asymptotically stable system. Okay, so only in the real positive case the system would be unstable. In the rest of the cases, it would be a stable system. Okay, let's move to the next question. So the amplitude of an undamped single degree of freedom system subject to an initial velocity b and initial displacement b and initial velocity 0 is given by. So undamped single degree of freedom system and initial displacement b and initial velocity 0. So if it is an undamped system, the solution is usually of the form is without damping or undamped system. And this P and Q we can find based on initial conditions. If you have a damped system, the initial solution would take the form with damping. So since it is an undamped case, we will take this case. Now what is given? We have given initial displacement B. So x of 0 is equal to B. So if you substitute that P sin 0, so P into 0 plus Q cos 0 1. So this is equals to Q. So displacement Q is equal to B. Now it's also given initial velocity is 0. What is initial velocity? X dot of 0. So since we know x of t, what is x dot of t? So it's a derivative. So P omega cos omega t minus Q omega sin omega t. The initial velocity is given as 0 and time t equal to 0. So this would be P omega equal to Q omega sin omega t sin 0 0. So 0. That means P is equal to 0. So the displacement equation would be x of t is equal to P is 0 and Q is B. B cos omega t. So what should be the displacement amplitude? Equal to B. So as you see here, the initial displacement B actually becomes the displacement amplitude if you are not giving any velocity in a single degree of freedom damping system, spring mass damper system. Okay. Let's move to the next question. So unbalanced force of magnitude 200 sin 10t newtons is transmitted to the base through a damper of stiffness 1000 Newton per meter and a damping factor of 0.5. What is the magnitude of force transmitted to the base if the mass of the machine is 5 kg? So this is how much force is getting transmitted from the machine to the ground. So you have given the force magnitude, unbalanced force magnitude, stiffness, and the damping factor, the mass of the machine. The formula for force transmitted to the base from machine is force transmitted by force generated is eta r whole square plus minus r square whole square 2 zeta whole square, where r is omega n by omega f, the frequency ratio, zeta is the damping factor given. In this case, because there is no forcing frequency and the frequency of the machine is actually transmitted to the base, the frequency ratio is actually 1 and the damping factor is 0.5. Then ft by f naught, the ratio is 1 plus 2 zeta r, so 2 into 0.5 into 1 whole square plus 1 minus 1 square whole square plus 2 into 0.5 into 1 square, 2 into 0.5 1, so 1 plus 1 by 1 minus 1 0, so 1, so root 2. So the actual force transmitted would be F3 is equal to root 2 into the magnitude of force generated is 200 newtons. So into 200, so it will 282 newtons force would be transmitted to the base. Okay. This is the force transmitted from to the base from the machine. Okay, let's move to the next question. Which factor is defined as the ratio of peak value to RMS value of signal? Form factor, B crest factor, skewness, D kurtosis. So which factor is defined as the ratio of peak value to RMS value of a signal? Form factor is actually RMS by mean, and crest factor is maximum by RMS, and skewness and kurtosis depend on the shape of the function. You can estimate them. So the factor ratio of peak value to RMS value is crest factor. Okay, maximum to RMS. Okay, let's move to the next question. What would be the Nyquist rate for the signal x of t is equal to 5 sin 100 pi t? Options are 50, 100, 200 and 10. So what should be the Nyquist rate or sampling rate for the signal? So the Nyquist rate or sampling rate, as we know, should be two times the maximum frequency in the signal, right? Okay. Now what is the maximum frequency in the signal? So first we should get that. So normal form for signal is omega is 2 pi f, and here it is 100 pi omega t. So f is 50. So what should be the Nyquist rate? 2 into 50 into 100 hertz. So the Nyquist rate should be 100 hertz. Okay, so this is how you can calculate the Nyquist rate if you know the frequency in the given signal. Okay, let's move to the next question. A 12-bit data converter has a resolution of, the options are 0.001%, 0.024%, 0.39%, 0.08%. So what should be the resolution for a 12-bit data converter? So this formula we know, we have discussed in the class many times in the sessions. So the resolution is 1 by 2 power n, usually range by 2 power n, because here we are talking about the percentages, so we'll just take 1. So here we have 1 by 2 power 12, so 1 by 1 by 2 power 12, so we have 4096. So 1 by 4096 will be 0.00024. So if you are writing in terms of percentages, so you can do resolution in percentages. So we divide it into multiply into 100, so 0.024 percentage. Okay, so this is basically this into 100 gives you a resolution in percentage. Okay, now let's move to the next question. In analog to digital converting system, the quantization can be reduced by option A, increasing sampling frequency, B, decreasing sample frequency, C, increasing number of bits, D, decreasing number of bits. So how can we reduce the quantization error? So what exactly is quantization error? So during analog to digital conversion, based on the resolution of the digital or based on the bit size of the storage system, of the data storage system, a specific resolution will only be available. So this resolution is arranged by 2 power n, where n is the bit size. Okay. Now the values which are actually lower than, since the analog values whose difference is less than the resolution are not differentiable anymore. Hence, if the two values, let's say you have a resolution of 1, so 1.1 and zero point 0.5, whose difference is 0.6, are same, but they are actually different. So won't be differentiable after analog to digital conversion, causing error known as the quantization or distillation error. So if you increase the resolution, then if you reduce the resolution, then this error can be reduced. So the resolution can be reduced by increasing the n. So increasing n decreases resolution, thereby reduces quantization error. Okay, so the answer is increasing the number of bits of the storage system will reduce the quantization error. Okay. So now let's move to the next question. Okay, so now let's move to the next question. The beat frequency is 1 hertz and the frequency of one signal is 20 hertz, then what could be the frequencies of the other signal. So in a beating system, you have one frequency 20 Hz and the base frequency 1 Hz. What should be the frequency of the other signal? So what should be the frequency of the other signal? What is formula for beat frequency actually? So absolute difference of between the two frequencies, right? So here it is given as 1 Hz and one signal is given as 20 Hz. So 20 minus f2 is 1. So when you have absolute, you can have 20 minus f2 is equal to 1 or 20 minus f2 is equal to minus 1. So f2 is 20 minus 1 or 19 Hz or f2 is equal to 21 Hz. Okay, so both are possible. So the answers are both A and B. So this is how you can estimate the one of the frequencies if you know the beat frequency and one frequency, or if you know the two frequencies, you can estimate the beat frequency. So this is one way to identify the frequency of the signal if you don't know. If you don't know the frequency of an incoming signal, and if you have a signal generator, you can use this phenomena to generate multiple frequencies and see if that frequency is matching. If there is any production of beat, if beat is forming, then the frequency of the incoming signal is also in the range where you are generating the frequency. Okay, let's move to the next question. How many operations, how many number of operations are required in fast Fourier transform of a data set with n number of points? So what should be the options are A n, B n log 2n, C n square, D none. So many operations are needed when you need to do FFT of a data set with n number of data points. So when you are doing FFT, you need to only perform n log 2 base number of operations. But if you have DFT, discrete Fourier transform, then you need to do n square. So that's why FFT is faster than the DFT. Okay. How many operations are required in FFT in a data set with n number of points? N log 2 base n log 2. Okay. So let's move to the next question. Due to a slower sampling rate, the original signal appears to be a low frequency signal. This error is known as the options are quantization error, B aliasing error, C leakage error, D. So if you have a slower sampling rate, that means let's say if frequency of the signal is 100 hertz, but you are sampling at only 50 hertz, then the original signal might look like a 50 hertz signal or 40 hertz signal, the original 100 hertz. So you are recognizing a signal as some other signal, it's getting aliased, so it's called an aliasing error. Okay, quantization error, as we discussed earlier, is due to the analog to digital conversion, and leakage error happens when because of the signal connection in between there might be a sudden jumps or differences based on the window of data collections. When you are recognizing a high frequency signal as a low frequency signal, then that error is the aliasing error. Okay, let's move to the next question. So during conversion of a bipolar signal of amplitude 5 volts from analog to digital values, an ADC with an amplitude resolution of 1.25 is used, 1.25 volts. What is the bit size required for the binary data record? So here the important things are bipolar, amplitude 5 volts, the resolution 1.25 volts. We are asking the bit size n. So we are given amplitude as 5 volts and bipolar signal. So the range would be 10 volts. Bipolar, so 5 to minus 5. So the range is 10 volts. Now the amplitude resolution is range by 2 power n is given as 1.25 volts. Range is 10 by 2 power n is equal to 1.25. So this gives 2 power n equal to 8. So 2 power n is equal to 2 cube, and which implies n is equal to 3. So this is a 3-bit size type storage system. Okay. So this is why even if you are given the resolution and the range, you can estimate the bit size which is used. Or if you know the bit size, you can calculate the resolutions. Okay, let's move to the next question. Independent signals which are not correlated has a coherence value of options 0, 1, -1, none. So two independent signals which are not correlated at all should have a coherence value of, so if they are completely independent, then the coherence value is 0. Okay, so usually the coherence function gamma x square is between 0 to 1. So if it is 0, signals are not correlated at all and are independent. And 1 implies a strong cause and effect relationship. Or they are just strongly correlated. Okay. So if they are independent, then their coherence value should be 0. The Q frequency in system analysis is equivalent to time. True or false? The Q frequency in substance analysis is equivalent to time. Answer is true. So in substance analysis, you would finally have the function as a function of Q frequency, which is so as a function for this is a Fourier transform, and then you take log of that, and of that you put Fourier inverse Fourier transform. So this is inverse Fourier transform. And this tau is the Q frequency which is equivalent to time. Okay. Substance. So a signal is given by sine of 200 pi t plus cos 200 pi t plus sine 400 pi t. What should be the Nyquist rate? So Nyquist rate, as we have seen, it should be twice the maximum frequency. So here, what is the maximum frequency? This one. So 200 2 pi f is 400 pi, which implies f is equal to 200. So this is the maximum frequency in the signal. So which implies Nyquist rate 2 into maximum frequency to 400 hertz. Okay. What should be the Nyquist rate? In this case, 400 hertz. Let's move to the next question. A device provides peak vibration of 30 meter per second square at 100 radians per second. What should be the peak? What would be the peak velocity? So usually, as we have seen earlier, the options are 30 meters per second, 30 mm per second, 3 meters per second, and 3 mm per second. So we have given peak vibration and the frequency. What should be the peak velocity? So what is the amplitude, x amplitude? If it is a, then x dot amplitude is a omega, and x double dot amplitude, acceleration amplitude, is a omega square. So here a omega square is given as 30, and what is the velocity amplitude? So velocity amplitude is equal to acceleration amplitude by omega. We can write it this way from these two. So it's 30 by 1000 divided as 30 meters per second. So 30 mm per second. Okay. So here we can write this a omega into omega. So a omega is the velocity amplitude. So velocity amplitude is acceleration amplitude by omega. Okay. Let's move to the next question. Which device can we use it to measure percentage composition of chemical elements? Atomic chemistry and spectrophotometer, atomic absorption spectrophotometer, both can be or not. So what will give us the percentage composition of the chemical elements? So atomic absorption spectrophotometer can actually give us the percentage composition. Atomic emission only gives which elements are present. Whereas atomic absorption can give percentage of chemicals also. Okay. So we need to use atomic absorption spectrophotometer. So which of the following is more suitable for using at higher temperatures? Strain gauge based accelerometer or piezoelectric based one or LVDT, or none of them are useful for high temperatures. Which is more useful for higher or more suitable for using at higher temperatures? Piezoelectric is more suitable for higher temperatures because it is made from ceramics which have very low thermal expansion coefficients. So they can stay stable at very high temperatures, so they are more suitable for higher temperature reasons use cases. Okay, now let's go to the next question. What is the dynamic range for a transducer that can measure a bipolar signal of amplitude 5 volts with a resolution of 1.25 millivolts? So what is the dynamic range for a transducer that can measure a bipolar signal of 5 volts with a resolution of 1.25 millivolts? The options are 18 decibels, 72 decibels, 78 decibels. So what is the dynamic range? And you know the range and resolution. So it is given by 20 log 10 range by resolution. So here it's given as bipolar signal with amplitude 5 volts. So the range is 10 volts and the resolution is given as 1.25 millivolt. So dynamic range 20 log 10 by 1.25 millivolt. So 1.25 into 10 power minus 3 volts. So 20 log 10, 8000. Okay. So this turns out to be 78 decibels. This is the dynamic range. Okay. So is you can estimate the dynamic range if range and resolution are given. Okay, let's go to the next question. Calculate the sum of two sound pressure levels. 30 dB and 32 dB. Options are 32 dB, 34.12 dB, 35.25 dB, 31 dB. Okay. So when you have two sound pressure levels, each 30 dB and 32 dB, what should be the effective sound pressure level? So this we have discussed in the corresponding week. So when you have two sound pressure levels, or if there are n, so the simple formula is 10 log 10 sum of how many ever they are. So this is how you can get the effective sound pressure level. So here we have SPL1 as 30 and as 32 dB. So effective equivalent SPL is 10 log 10, 10 power 30 by 10 plus 10 power 32 by 10. So 10 power 3 plus 10 power 3.2. So it's almost 2585. This is almost. So this comes around 34.12 dB. Okay. So this is the SPL equivalent. So this is the formula when you have to combine multiple SPLs to get the effective SPL at a given location. Okay. Let's move to the next question. Calculate the lower frequency of a 1 by 3 octave filter if the center frequency is 31.25 Hz. So here 1 by 3 octave filter, and we should calculate and the center frequency is given, we should calculate the lower frequency. The options are so what should be the lower frequency in a 1 by 3 octave filter if the center frequency is 31.25 Hz. So given 1 by 3 octave filter and the center frequency as 31.25 Hz. So lower frequency usually is 1 by 1 2n into Fc center frequency, and F upper is 2 power 1 by 2n into Fc. So this is the formula if you know the center frequency to get the lower frequency or the upper frequency. So here 1 by 2 1 by n is 3, 1 by third octave filter into 27.84. So this is 31.25. So this actually comes to 27.84 Hz as the lower frequency. So the other related formulas also we have discussed in the corresponding week, so you can check there. So this is how you can get the lower frequency from Fc and upper frequency from Fc. And one more relation is Fc is equal to square root of Fu into F12. Okay, so now let's move to the next question. So why does shaft misalignment occur? Looseness of the rotating components or offset present either by lateral or angular amount, or due to the presence of internal crack, or due to the rubbing of rotating machine components. So the shaft misalignment actually occurs due to the offset present either by lateral or angular amount. So if there is one shaft and the other shaft is like this, then there is a misalignment. Or if one shaft is this way and the other shaft is this way, there is misalignment. So these actually lead to the shaft misalignment. Offset present either by lateral or angular amount. Okay. Okay. So let's move to the next question. Which of the following is true for eccentricity of rotors? Eccentricity in rotors for electrical machines. So which of the following is true for so which of the following is true for eccentricity in rotors for electrical machines? Creates an increase in radial vibrations at twice the rotational speed or equal to the rotational speed or axial vibrations at twice the rotational speed. So eccentricity in rotors actually causes increase in vibrations in radial vibrations at twice the rotational speed and not at the rotational speed, at actually the twice the rotational speed, and mostly in the radial vibrations the eccentricity leads to, not the actual vibrations. Okay. So let's move to the next question. Which of the following method is suitable for balancing multi-stage turbine blades? A. Static balancing. B. Dynamic balancing. C. Both or none. So which of the following methods is suitable for balancing multi-stage turbine blades? So in multi-stage turbine blades or any multi-stage systems, the unbalances will create both forces and couples in different planes. So you need to balance forces in each plane. So that is called which is the dynamic balancing. If the entire system is in a single plane, then it is the static balancing. Okay. So in multi-stage turbulence, both force and couples will be generated in different planes. So you balance out the force in each plane. So at the end there won't be any couples because every plane the forces are balanced. So this is called the dynamic balancing technique. So this is the dynamic balancing. Okay. On to the next question. So when you have three unbalanced masses rotating at a constant speed in a single plane. So because it's a single plane, there are no couples or moments getting generated. So you only need to balance the forces, and that should be enough. So even if you are doing a dynamic balancing, you balance out the forces in in each individual plane. So you don't have to balance the moments actually. Okay. So only the forces should be balanced, and that is enough. Okay. Let's move to the next question. What would be the vane pass frequency VPF at 1800 RPM for a pump impeller with 30 vanes? So a pump impeller, a roller with 30 vanes, what should be the vane pass frequency? So vane pass frequency is RPM by 60 into number of pins. So RPM here is 1800 by 60 and the number of pins is 30. So the band pass frequency would be 900 hertz. Okay. So this is how you can estimate the band pass frequency. Okay. Let's move to the next question. Gear of 30th is rotating at 1200 RPM. Calculate the gear mesh frequency. The options are 20 Hz, B 40 Hz, C 600 Hz, D 300 Hz. So what should be the gear mesh frequency if a gear of 30 teeth is rotating at 1200 RPM? What should be the gear mesh frequency? So RPM by 60 into number of teeth. So 1200 by 60 into 30. 600 Hz. So this is how you can estimate the gear mesh frequency. Now let's go move to the next question. Determine the engine firing frequency for a 4-stroke 4-cylinder engine when the output shaft rotates at 1800 RPM. Options are 30 Hz, 50 Hz, 60 Hz, 72 Hz. So what should be the engine firing frequency for a 4-stroke 4-cylinder engine rotating at 1800 RPM? That is it. So engine firing frequency is RPM by 60 into number of cylinders into 1 by K, and K is 2 for 4-stroke, 1 for 2-stroke. So engine firing frequency, so RPM is 1800 by 60 into number of cylinders 4 and 4-stroke, so 1 by 2. Okay. So the engine firing frequency is 60 volts. Okay. So is the engine firing frequency for a 4-stroke 4-cylinder engine, and the output shaft rotates at 1800 rpm. Okay, now let's move to the next question. So which of the following is a contact type temperature measurement device? So which of the following is contact type? Pyrometer is a not non-contact type. Even IR camera is a non-contact type. So thermocouple is a contact type. Contact type temperature measurement device. Okay. Let's move to the next question. Static eccentricity is not caused by mobility of stator core, incorrect positioning of rotor or stator, or bent rotor shaft. So if you have an ovality of the stator core and incorrect positioning on the stator rotor, there will actually be an eccentricity. But when you have a bent rotor shaft, you will actually have a dynamic eccentricity as it is rotating. So static eccentricity is not caused by a bent rotor shaft. The other two will cause static eccentricity, but bent rotor shafts actually causes dynamic eccentricity. So that's the answer. Okay, let's move to the next question. Which fault identification technique is best suited for submersible pumps? A. Vibration monitoring device, or motor current signature analysis, thermography, none. So which is more suitable for a submersible pump? So a pump is under water or under air, submerged inside. So which is more suitable? So in vibration monitoring, you need to have accelerometers and all. So it is not suitable. In thermography, you need a specific distinction of a temperature rise. But if you have a submersible system, then the temperature rise might be very less. So it's not that suitable. So the suitable one is actually motor current signature analysis, where the current to the motor is tracked as a function of time. So if there is any fault, the current signal actually changes. So it is suitable, more suitable in this case. For example, submersible pumps underground, buried underground, or in nuclear reactor. So these are more useful. Motor current signature analysis based technique. Let's move to the next question. So which of the following technique can be used for crack detection in non-conductive materials? A. Ultrasonic. B. Eddy current based technique. C. No. So which of the following technique can be used for crack detection in conductive material, non-conductive materials? So eddy current is works through magnetic induction. So it needs conductive materials. But ultrasonic, there is no need for conductive system. So it can be used for crack detection in non-conductive materials. So the technique used for crack detection in non-conductive materials is ultrasonic. It is more suitable. So which of the following devices can be used for measuring vibration in railway locomotives? Microphone, accelerometer, or both? Microphone and accelerometer, or none of these two. So which can be used for measuring vibration in railway locomotives? So for railway locomotives, you should actually use vibration. So you should use an accelerometer, and microphone doesn't work to measure the vibrations. It is mainly useful for sound. Okay. Okay. Now let's move to the next question. So eddy current technique is based on which phenomena? I have just explained the phenomena further. I just discussed it. Eddy current technique works in conductive materials and works on the principle of magnetic induction. So the changing currents or changing electric fields can generate a magnetic field, which in turn can generate current. So that's how the eddy current technique works based on the principle of magnetic induction. Okay. So yeah, that is the last question for today. Hope this gives you a good revision before the exams. And in this week we have actually covered in this session we covered many questions from all the topics. Okay. Thank you everyone. Thank you for attending these sessions. If you have any questions, you can ask in the in the discussion forum. And mostly this might be the last time we will meet. Thank you. Thank you for attending these sessions. So hope you learned some new things. Thank you and goodbye.